All right, so now we've learned how to do derivatives of any exponential and logarithmic function. You may be wondering, what else is there to this section? Well, we do have one more topic. It is a sort of an extended technique of differentiation called logarithmic differentiation. Essentially, what we're going to be doing is we're going to be taking the idea of implicit differentiation and combining it with properties of logarithms in some clever ways to allow us to take the derivative of a type of function we as of yet are not able to do. So I want to introduce this by looking back on what we've done. So we have established the power rule, which allows us to take the derivative of a function that looks like x to the power n, where n is some number, right? And we have, this is n x to the power n minus 1. Great. We have now a rule for taking derivatives of exponential functions. I'm going to call the exponential rule. And it says if you have n to the power x, or a number raised to the power x, then you can differentiate that by doing n to the power x, then times the natural log of n. Okay, so these are two different functions. In one case, the variable is the base of the exponential expression. In the other case, the variable is the power of the exponential, right? So a power rule is for power functions. Power functions are where it's x raised to a power, right? Constant power, but exponential rule for exponential functions, where the base is the constant and the power is where the variable is. So I just want to be very clear. You have these two types of functions, and they have two very different rules. So the question is, what about the derivative of x to the power x, where both the base and the power are the same variable? What about that? Derivative of x to the power x. It's not a power function, so we can't apply the power rule, right? We can't just do the power rule of this. Also not an exponential function, we can't apply the exponential rule. It is a different thing. So here's how we can approach it. Like I said, we're going to use implicit differentiation. So we're going to start with y equals x to the power x. Our goal is to find dy over dx. However, before we start implicit differentiation, we're going to do some rules of logarithms. We're going to do the logarithm, the natural log in particular, because it's the easiest one to work with. We're going to do the natural log of both sides of this equation. One of the reasons this is a valid step is because x to the power x as a function really only gives you positive numbers. It's only really valid if x is a positive number. If x is a negative number, then you get all sorts of wacky behavior, including things like complex numbers. So we're going to take it as an assumption here. We're going to assume x is a positive number. Okay. I'll just show you real quick on Desmos here what this function looks like, just so you have a picture in your mind. X to the power x looks like this. So like I said, did you see all that? Oh, it disappeared. There was some sort of, it was graphing some points on the left side. It just was kind of just got pretty confused. There's a lot of complex numbers that show up when x is negative. We're just going to have positive values over here, not even 0. I think for 0, it says it's equal to 1, which is fine because it certainly is approaching the value of 1, but we're really just specifically talking about positive numbers. That's the function. All right, set that aside. Okay, so now we've done our logarithm of both sides. We're going to use a property of logarithms where you can take an exponent like this x up here, bring it outside the logarithm as a constant multiple, x times the natural log of x. You may remember that as one of our exponentiation, like exponent rules. We got that. So then what we're going to do next is apply implicit differentiation. So we're going to say implicit differentiation with respect to x. Okay. On the left side, derivative of the natural log of y requires the chain rule because it's consistent with y being a function of x. So we do the derivative of the natural logarithm function first, which is 1 divided by its input. We learned that in the last video. Then we multiply by the derivative of y with respect to x. Now on the right side of the equation, we have just functions of x. So that should be easier, but it is a product. So we have to apply the product rule. I'm just going to put product rule f prime times g plus f times g prime right above there. And then we'll do the derivative of, well, I guess I'll label these. This is like our f and this is like our g being multiplied together. So the derivative of the first function would be 1 times the natural log of x, and then plus the first function x times the derivative of the natural log of x, which is 1 divided by x. All right. So in our next step, I'm going to take both sides of this function and multiply them by y. Like that. Okay. And what that's going to have the effect of doing is canceling out the y, and we'll solve for dy over dx. There's a little bit of simplifying we can do here. We have natural log of x plus, and then instead of writing x times 1 divided by x, I'm actually just going to write plus 1. There we go, just plus 1, because x times 1 over x is, I can't do that, right? And then the last thing I'm going to do, instead of writing times y, I actually know what y is equal to as a function of x because we were given it right up here. And that's what we started with, was y equals x to the power x. So that can come down here and substitute in place of that y. So I'm going to write times x power x. And that is our answer, folks. That is the answer to this big question. It is the derivative of x to the power x is that function. It's a complicated thing. Natural log of x plus 1 in parentheses, and then multiply by x to the power x. And that gives us what we want. So this strategy that we've used here is an example of what we call logarithmic differentiation. So what is logarithmic differentiation? Here it is, logarithmic differentiation. Here, it kind of has 2 steps. One, set up an equation. Set up your function in the format of an equation, like y equals blah, 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 blah. And then 2, natural log both sides of the equation. And we use natural log because its derivative is simpler than using log base 2 or log base 10 or anything like that. Just log natural logarithm because it's convenient. Then step 3 is to simplify with log rules. Okay, so in particular, that happened right here. Here is where we applied step 3. You see how we brought the, actually that was where we applied step 2, I guess. The next line is where we applied step 3, because we simplified it by taking the power and bringing it outside of the logarithm function, right? That was applying a log rule. And then step 4 is to do implicit differentiation. And then step 5 is to substitute back in whatever function you were working with, y equals blah, 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 what you had, right? You substitute that back in term for the y that you get. And that's it. That's that's logarithmic differentiation. So I'm going to end this video there, and we'll probably look at some other examples of this in the future. That's as much as I've got for now.